is, looking down here, we have the electromagnetic spectrum. Notice that the higher energy things like X-rays and gamma rays have a shorter wavelength than lower energy things like radio, microwave, infrared. So as you move this way, energy increases and the wavelength shortens. As you move this way, energy decreases and wavelengths increase. Galaxies. So 3 types of galaxies. Now, there are more than 3 types of galaxies, but this is a simplified explanation because we don't need to go into like type 2A spiral galaxies and type 1B irregular galaxies. You just need to know the 3 types: spiral, elliptical, and irregular. Now, let's start with spiral galaxies. So for spiral galaxies, our own Milky Way galaxy is a type of spiral galaxy. It's called a barred spiral galaxy. And spiral galaxies tend to make up most of the galaxies in our visible universe, at least from what we can see nearby us. Let's call it our local group. Anyway, our Milky Way galaxy is spiral, and it's kind of like this one. They tend to be more flat, kind of like pancake shaped, and they are wider than they are tall. And they also contain nebula, which means new stars are being formed. And actually, in our own Milky Way galaxy, new stars are being formed pretty much every day. So spiral galaxies are, quote unquote, the newer type of galaxies. They only appeared starting, or at least appeared in big numbers, starting about 10 billion years ago. So even though our own Milky Way galaxy is about 13 billion years old, it wasn't always a spiral galaxy. It's changed over time. And in fact, it'll change again. In about 4 billion years, the Andromeda Galaxy will smash into the Milky Way galaxy, and it won't be a spiral anymore. Neither of them will be. They'll probably be an elliptical galaxy at that point. So galaxies can change. They're not static. They don't stay the same forever. In our own galaxy, it actually does that too. So that's spiral galaxies. What are they? Spirals. They contain nebula. They're kind of pulled together by gravity. Next, we have elliptical galaxies. So elliptical galaxies, think of it like round or football shaped, circular. So unlike spirals, which are mostly flat, these are more of a circle, or I guess a sphere is a better way of putting it. Now, most elliptical galaxies don't contain as much nebula as a spiral galaxy would. So elliptical galaxies, a lot of them tend to be done making new stars, which means they're pretty much at the end of their lives. They're going to just get dimmer and dimmer over time. Now, that's not for every elliptical galaxy. For example, when our own Milky Way becomes an elliptical galaxy in about 4 billion years, it'll have plenty of new gas and dust from the collision between the 2 galaxies. So just not every of them. Know that only some of them don't contain any nebula. They make up about a third of all galaxies, and some of the very first galaxies were elliptical because it's not that hard to make a circular shape. It does take a little bit of time to allow gravity to compact them into that sphere, but other than that, it's a pretty quick process to make it. Now, we talked about spiral, we talked about elliptical. Let's talk about irregular. It's the one that doesn't really have a defined shape. They could be somewhat circular, they can be somewhat flat, they can have tendrils coming off. Anything that doesn't fit into the other two, we're going to call irregular galaxies. Now, what are they? They're stars and dust, just like any other galaxy. They also usually tend to have lots of nebula. And here's the thing that's most important for us. Most early galaxies were irregular. When you have just a random clump of stars, it doesn't take time to make a random clump of stars. As soon as you have a random clump of stars, you've got a galaxy that's irregular. It does take time, however, to take that irregular galaxy and turn it into a sphere. It also takes a lot more time to take that irregular galaxy and turn it flat and get it spinning. So spiral galaxies will take the longest amount of time to make. Gravity takes time to pull things together. Same thing for elliptical, although a lot quicker. And in the irregular, it takes no time at all because as soon as you have stars, you have irregular galaxies. So we will have less irregular galaxies as time passes. Because what's happening is these irregular galaxies are getting pulled into other shapes. It's not that they're going away, it's just they're becoming something new. All right, good, done. And in fact, I can show you on this picture right here. So in an expanding universe that's changing over time, like a universe is not staying the same, if we look at the early universe, it should appear less ordered, meaning there's less or more irregular galaxies in the past. And if we look, come back here, in the past, as we look really, really, really far back, we see a lot more irregular galaxies. And as we get closer or we look farther into the future or less into the past, we start seeing more and more spiral galaxies because the irregular galaxies are becoming spirals and ellipticals. And so what this tells us is if we look at those really, really, really far away irregular galaxies and we see a whole bunch of them, we know that the universe isn't staying the same. It must have been different in the past. And if we look at those irregular galaxies, we also notice something else. They're more redshifted. Now, if you don't know what redshifted is, stick around. That's coming up soon. But what that means is, in the past, those galaxies, more redshifted, that means they're moving farther away from us. And in fact, the farther back we look, the faster away from us they're moving. So we're about to look at an image, and in this image, the newer galaxies, the ones that you can actually see what shape they are, they're about 6 to 10 billion years old. But every single dot on this image is a galaxy. Now here's the thing, let's take a look. All of these right here, galaxy, 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 galaxy. Obviously, these are galaxies. But every single dot, that one, every dot that you can possibly see on this image is a galaxy, all of every single one of them. And in this image, pretty much every single galaxy is actually moving away from us in this image, all of them. This is a star right here, so that's not moving away from us, but everything else on this image is. And if you were to look at the wavelengths for these closed galaxies, the ones you can actually see the shape of, they're moving away from us somewhat fast, but nowhere near as fast as these faraway galaxies, all these little dots right here, here, and here, and here. So these ones are even moving faster. And you might be thinking, okay, well, if this is all the galaxies in the universe, that's fine, but it's not. That's not all the galaxies in the universe. That's all the galaxies in this tiny little patch of sky with the moon to scale right here. So this is this image that we just looked at. All the galaxies are contained in this small little patch right here. There are a lot of galaxies out there. Many, many, many galaxies. And here's the thing. They're all invisible to our eyes. Even if you could see, like if you had a really, really good visible light telescope, you would see none of these. They're moving away from us so fast that a lot of their light has been shifted into infrared and microwaves for some of the really, really far ones. So you couldn't even see these even if you could. So light has a speed. So like if you were getting into a car and you were trying to drive somewhere 10 miles away and you're going 30 miles per hour, same thing for light. If you're trying to get 10 billion light years away and light's going 300,000 kilometers per second, it's time to get any place. So light year is the distance that light travels in 1 year. If we're looking at a galaxy that's if we're looking at a star that's 500 light years away, well, that star, the light we see from it is 500 years old. So spectra, let's talk about it. We can use redshift to tell that the universe is expanding. Now, here's the thing. If we were to look at hydrogen light, this is a hydrogen lamp right here, if we were to look at it in a laboratory, these are the wavelengths we would see. We would see an emission wavelength at 655. We'd see a lighter blue at 480, a darker blue at maybe 440, probably a violet, and then two ultraviolet lines over here beyond 400. Now, if we look at a star or a nebula or something in our own Milky Way galaxy, something that isn't moving away from us, we'll see these exact same lines. So let's take a look. Here's a galaxy that is, a nebula that is not moving away from us. And notice these lines match up perfectly with these lines because, well, this nebula is in our own galaxy. It's not going anywhere. There's also some extra elements from some other light wavelengths from other elements like oxygen. Okay, but let's focus on this one right here, this hydrogen line. Now, this is in our own Milky Way galaxy. Let's take a look at what happens if we look at a galaxy that's moving away from us. So this galaxy, notice the line was here, but now it's over here. It started at 655, but it's moved 10 nanometers over to 665 over here, 665 nanometers. And so what that means is this galaxy is moving away from us enough to stretch that light out. Those wavelengths have actually lost energy and become longer. 655 is greater than 655. And this galaxy, we can actually use that to determine that it's moving about 4 million meters per second away from us. So it's moving really, really, really fast away from us, and that's stretched the light out. Okay, let's get farther. So here's the wavelengths for this star, or for this galaxy. Let's pick a galaxy even farther away. How about galaxy UGC 12508? Notice it was here, now it's over here. So the further away the galaxy, notice it looks smaller, the more shifted towards the red that light is. Let's go back. Our own Milky Way, farther away, let's get even farther away. So now galaxy KUG 1750, this galaxy even more redshift. It's at 690 nanometers. So let's take a look. Our own Milky Way, farther, farther, farther. Notice that peak keeps moving more and more and more to the right, more redshifted because red's over here. Let's get even farther. So here's this one. Now there's a galaxy that's so far away that that hydrogen line isn't even red light anymore. Notice it's now in this gray area, so it's infrared light. So the redshift caused by this expansion stretched the wavelength so much that it's not even red. Well, let's take a look. So Milky Way, farther, 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 and let's get even farther than that. So here's a galaxy that's even farther away. I don't think we're going to get much farther than this. This galaxy is moving away from us at about 10% the speed of light, 44 million meters per second. So about 10 times faster than that first galaxy we looked at. And you'll see the hydrogen line wavelength is way over here beyond 750. It's probably 755. So it's moved a whole 100 nanometers. But also you notice, look at these other colors that have popped up. These weren't there before. Let's go back and figure out where those were from. Those were actually from these over here. This violet and these two ultraviolet wavelengths have actually moved over so much that they've moved into the visible spectrum. So they're now yellow and green instead of violet and ultraviolet. So every wavelength, not just red gets moved over, everything gets stretched out and moved over towards red, towards longer wavelength, towards less energy. So we can actually use that to figure out how fast a galaxy is moving away from us just by looking at the spectral lines. Let's one more time look at our own galaxy, and then farther, 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 farther. Everything's moving more towards the red. So that's it. Those are our notes for today. Let's talk about